Hello everyone, welcome back to Physics 331. In our last video, we were doing a derivation of the Fourier transform and the inverse Fourier transform. And what the goal was to try to understand how we could go back and forth between the time domain of a signal and the frequency domain of that same signal when we were dealing with signals in time that were not periodic. So this would be, say, some pulse that had some arbitrary shape but was zero at very early times, and then to some non-zero value at intermediate times, and then back to zero at long time later. And we completed that derivation, and we worked out the Fourier transform in the red box here. And so if we knew the function of time f of t, we could evaluate the integral in the red box to come out with the function of frequency omega f hat. So along the way during that derivation, we also define the inverse Fourier transform. So that's in the blue box. And so in this case, if we knew f hat of omega, how the frequency dependence of whatever the signal is, we could evaluate the integral in the blue box and come out with the time dependence of that same function. So what I want to do today is I just want to work through a few examples of how we could actually implement this. And so the first example is going to be the box function. So we're going to define the box function in the following way. Often people use pi, the symbol pi, for this box function. And so this is going to be a function of time, and it's going to be defined to be 1 over the time range minus n times pi to plus n times pi. It'll be defined to be 1/2 right exactly at these boundaries, so when time is equal to plus or minus n pi. And it'll be 0 for times outside of this range, so we'll just say 0 otherwise. So it's relatively easy to plot this function, and so I'll do that here. Here's our time axis. Here's t equals 0. And we're going to plot our box function. And we just have to identify where n times pi and minus n times pi are. And so what our function looks like is it's 0 until we get to minus n times pi. Then it jumps abruptly up to 1 until we get to plus n times pi. And then it jumps down abruptly to 0 and stays 0. And so here is the value 1 is right there. Okay, so I may have drawn this a bit asymmetric, but it's a symmetric function. So what we have to know about n is just a multiplier of pi defining where our boundaries are. So if n is some small number, then we have a narrow pulse in time, and vice versa, or conversely, if n is large, we have a wide pulse in time. And so we'll use that fact a little bit later. But first of all we want to do is just evaluate this Fourier transform. So we're going to go from knowing the time dependence of pi to try to figure out what the frequency content of that signal is. And so the way we would evaluate this Fourier transform is we want to end up with a pi hat of omega, and that's going to be determined from the integral from minus infinity to plus infinity of pi of t times e to the minus I omega t, and this is going to be an integral over time. So once we evaluate this integral, all the time dependence will be gone, and we'll just have a function of omega. Okay, So the first thing we want to recognize is that pi of t is 0 when we're outside of the times minus n times pi to plus n times pi. And so this integral that we have to evaluate is equivalent to minus n times pi to plus n times pi of pi of t, which is equal to 1 in this time range. So pi of t is just going to be a 1. And then we have to multiply by the e to the minus I omega t and do our time integral. Okay, so that's fine. Then what I'm going to do is, before doing my integral, I'm going to use Euler's equation to express e to the minus I omega t in terms of trig functions. And so what we'll have to do is integrate from minus n times pi to plus n times pi. And this complex exponential we could write as cos omega t minus I times sine omega t, and then evaluate, then integrate with respect to time. Okay, so the integral of cos omega t is 1 over omega sine omega t, so we'll get a 1 over omega, and then we'll have a sine omega t. And then when we integrate sine, we'll get the same 1 over omega factor, so that's why I've already anticipated that by factoring out the 1 over omega. The integral of the sine is minus cos, but we have minus sine, and so overall we get a plus. The I is still there, and we get a cos omega t, and we have to evaluate this between our two limits. Okay, so let's just do this in a lot of detail here. So we're going to have a 1 over omega, and then we're going to have, let's see, sine omega n pi minus sine of minus omega n pi. And then we have plus I of cos omega n pi minus cos of minus omega n pi. So where we put in these two limits that we have. Okay, well, the sine function, sine of minus x is equal to minus sine of x. And so all of this just becomes plus sine of omega n pi. Cos of minus x is just cos of x. And so all of this becomes minus cos of omega n pi. And so that minus cos of omega n pi is going to cancel with the plus cos of omega n pi. And so we're going to get a cancellation here. Whereas in the first term, in the first couple of terms with the sine functions, they're going to add. And so what we'll end up with then is that this pi hat of omega is going to be equal to 2 over omega sine of, let's write this as pi n omega. Okay. And so we could express this if we wanted to as, let's see, I want to multiply the top and bottom by n pi. So we'll get 2n pi, and then we'll have sine of pi n omega divided by omega, but we have to multiply by n pi, so it's going to be pi n omega. And so the sine of x divided by x, that's typically defined as the sinc function. And so this is the sinc of n omega, is the way it's defined sometimes, where the sinc of n pi implies the sine of, the sinc of n omega implies the sine of n omega times pi divided by n omega times pi. Okay, and so this is going to be equal to 2n pi sinc of n omega. All right, so that's our first evaluation of a Fourier transform. So we started with a function of time, which was just this box function. Once we evaluated our integral, we ended up with a function of omega. And so pi hat of omega results from the Fourier transform of pi of t. Okay, so that's fine. What I'd like to do is I'd like to try to interpret these results a little bit. So I'm going to try to make a plot of our Fourier transform. So on our horizontal axis, let's see if I can make that a little bit straighter. So there's our vertical axis. Our horizontal axis is going to be n omega. And then this vertical axis is going to be pi hat of omega. And I'll just divide out that prefactor 2n times pi. So let's divide by 2n times pi. The sinc function, if you evaluate it carefully using L'Hopital's rule, at 0, at n omega equals 0, the sinc function evaluates to 1. And so right here is a 1. And then because the sinc function has the sign in it, it's going to oscillate, but we're dividing by pi times n omega. So as we increase n omega along our, say, horizontal axis, we're dividing by a larger and larger number. And so the size of these oscillations gets smaller and smaller as we go out to higher and higher frequencies. And so what that looks like is something like this. And it's a symmetric function, so we can go to negative values of frequency as well. And so it's some kind of function that looks a little bit like this. So what I want to think about is, when does the sinc function go to 0? So our zeros occur when the sine of pi times n times omega is going to be equal to some multiple of pi. So our zeros are when, well, of course, when sine of n pi omega is equal to 0, but that occurs when n pi omega is equal to, say, plus or minus pi, or plus or minus 2 pi, or plus or minus 3 pi, and so on. And so what we could do is divide by pi. So the condition for our zeros are that n omega is equal to plus or minus 1, or plus or minus 2, or plus or minus 3, and so on. Okay, and so we can identify these zeros. There's one here at n omega is minus 1, and another one when it's plus 1. So this would be the minus 2 case, and so over here would be plus 2, here's plus 3, and here's minus 3, and we could keep going. Okay, so what I want to think about here is kind of how can we characterize the width of this sinc function? Well, one way to do it is to find the range of frequencies between the first two zeros on either side of n omega is equal to 0. Okay, you can see that's where what our Fourier transform tells us is the amplitude of the various frequencies that are used to make up this pulse in time. And so when pi hat of omega is large, there's a large contribution from that particular frequency. And so the largest contributions come from frequencies that are within this window that lie within this red arrow that we've called the width of our function, pi hat of omega. Okay, so note that the characteristic width of pi hat of omega, which was 2n pi times the sinc function of n omega, is something like n omega falls between plus and minus 1. And so if we divide by n, then omega lies between plus and minus 1 over n. So there's two cases, of course, to consider. One is small n. And so when n is small, then 1 over n is large. So we'd have a large span of frequencies. So this is a wide omega. So small n means we have a wide range of frequencies contributing to pi hat of omega. So we have a large range of frequencies contributing to pi hat of omega. But let's go back to the beginning and look at what n was telling us for our pulse in time. We said if n was small, then the width of pi of t was small, and so it's a short pulse in time. Okay, and so small n means a large range of frequencies, but it also means a short pulse in time, which is determined from this pi of t. Okay, we could also look at the other case, where we have large n, and you can see where this is going to go. When we have a large n, the 1 over n is small, and so we have a narrow range of frequencies. So we have a kind of narrow omega range. So we have a small range of frequencies in pi hat of omega. But of course, if n is large, that means our pulse in time is long. So a long pulse in time in pi of t. Okay, and so these observations, we've only done one example, but these observations are going to be generally true. If we have a pulse that is narrow in time, there's a wide range of frequencies that are contributing to that pulse in the frequency domain. On the other hand, if we have a pulse that's very large in time, takes a long time to rise up and then to decay back down to 0, then the range of frequencies contributing to that signal in the frequency domain is very narrow. Okay, good. So that's our first example. Our second example will take this previous discussion to the extreme. And so that's going to be the delta function. And so a delta function is infinitely narrow in time. And so let's see what happens when we take the Fourier transform of the delta function, delta t minus t naught. Okay, so if I was to plot this delta function in time, and if this is 0, and this is going to be delta t minus t naught, this function will be 0 everywhere except it'll be an infinitely narrow pulse, or let's say an infinitesimal width, and that will occur at exactly the time t0. Okay, the nice thing about delta functions is that when you have an integral where with a delta function in the integrand, it's generally very easy to evaluate that. And so we're expecting, I think, that to calculate our Fourier transform will be quite simple. So the Fourier transform of our delta function, or let's just write generally the Fourier transform of any function of time, is f of t times e to the minus I omega t integrated over time. Okay, well, so in this case, our f of t is just the delta function, delta of t minus t naught, e to the minus I omega t, and integrate with respect to time. And what the delta function does is it just takes everything else in the integrand and just evaluates it at the time t equals t naught. And so the result is quite simply e to the minus I omega times t naught. And that's it. So a couple things we can notice. One is that the f hat of omega is complex. I think what we'll do is in our last example of this video, we'll think a little bit more about what a complex f hat of omega really means. But for now, what I'd like to do is just to evaluate the magnitude of f hat of omega. So in fact, first we'll evaluate the square of the magnitude, which is just going to be f hat of omega times the complex conjugate of f hat of omega. And so that's just e to the minus I omega naught t, that's f hat of omega, and the conjugate just changes the sign in front of the I. And so when you multiply these two exponentials together, we just get 1. And so that means that f hat of omega magnitude without the square is also just 1. This is frequency independent. Or in other words, that f hat of omega is just constant in frequency. Its value is the same at all frequencies. So that if we were to plot this f hat of omega magnitude as a function of frequency, it's just a flat line. And so that flat line in this example just sits at 1. Okay. And so if you think about this, this is actually consistent with what we saw from the box function, because we saw in the box function, as we shrink the pulse width in time, we expand the range of frequencies in the Fourier transform. And so now, in this extreme case, we've taken that pulse width and shrunk it to 0, and now our range of frequencies is infinitely large. So an infinitesimally narrow pulse in time contains equal amounts of all frequencies in f hat of omega. So what I mean by equal amounts is that the magnitudes of all of the different contributions at different frequencies are the same. So that's the f hat of omega having the same value at all frequencies omega. Okay. Before we leave this example, we can do a fun thing. We've now evaluated two Fourier transforms, but we haven't evaluated any inverse Fourier transforms. And so what we're going to try to do is evaluate the inverse Fourier transform of f hat of omega is equal to e to the minus I omega t naught, which is the example that we just worked out. So inverse Fourier transform of a flat frequency spectrum. Okay, and so again, we're just going to use the example that we just did. So i.e. f hat of omega magnitude is just 1, and f hat of omega is e to the minus I omega t naught. Okay, what we know already from the previous example, so we already know that f of t must be equal to the delta function, because we just took the Fourier transform of this delta function, and what we got was e to the minus I omega t naught. And so if we take the inverse Fourier transform, we must get back to the original f of t. Okay, but let's just see what happens if we try to calculate this. First, let me just remind you what the inverse Fourier transform looked like for any function f hat of omega. What we have to do is we have to integrate over all frequencies f hat of omega times e to the, this time it's the plus I omega t, and it's an integral over frequency, and there's a 1 over 2 pi out front of the integral. Okay, so there's the 1 over 2 pi and the integral. F hat of omega we know is e to the minus I omega t naught, and then we have to multiply by e to the I omega t and integrate with respect to frequency. So we can combine these two exponentials. So it's e to the, let's see, I omega, and then it's t minus t naught, if we get the signs right, and d omega. Okay, but like we already said, we already know that the f of t is the delta function, t delta of t minus t naught, and so therefore it must be the case that, delta of t minus t naught is equal to 1 over 2 pi e to the minus infinity to plus infinity of e to the I omega t minus t naught, and integrate over frequency. And so what we've come up with here is one way of coming up with a mathematical expression for the Dirac delta function. So this is one way to express the delta function mathematically. So in fact, one of the reasons I've did this is because I think we're going to make use of this result maybe a week or two down the road. Okay, so just keep this in the back of your mind. Okay, good. So I want to do one final example. And so this one final example is going to be, again, it's going to be another Fourier transform, and it's going to be exponential. So the final example for today. We're going to have an f of t, so maybe we could just call it something. So the exponential decay. So we'll define our f of t to be let's say some amplitude, we'll call it V naught, e to the minus t over tau. And so this will be true for t is greater than or equal to 0. And then otherwise, f of t will be 0. So this is for all negative times f of t is 0. I've used some notation here intentionally. So if we were to have like say we were to have a charged capacitor, and then we were going to connect it in parallel with a resistor using a switch. So once we close the switch, the capacitor discharges through this resistor, and we know that that discharge would be an exponential decay if we were to measure, say, the voltage across the capacitor. And so, you know, an example, a physical example that you could have in mind is the voltage across a capacitor discharging through a resistor, right? And so it might look something like so maybe we're measuring the voltage across this capacitor, which is initially charged up. And at t equals 0, we throw the switch S down, and the capacitor starts to discharge, and that voltage would decay exponentially. And what it would look like is, here's our time t, here's our f of t. At t equals 0, we're going to have v naught, and that's going to decay exponentially. Okay, what's a little bit different about this function is that if we were to actually do the circuit that I drew, the voltage would be a constant V naught at all times before t equals 0 and then decay exponentially. So our pulse admittedly is a little bit different than that. It jumps from 0 to V naught at t equals 0 and then decays exponentially after that. We can identify a couple other points on our plot. So this is going to be our V naught. When t is equal to tau, we have V naught e to the minus tau over tau. So it's V naught over e. And so V naught over e is somewhere maybe around here. V naught over e, and this occurs at the time t is equal to tau. Okay, so let's just go ahead and work out this Fourier transform. F hat of omega in general is this integral of f of t times e to the minus I omega t dt. So putting in our f of t, we have v naught e to the minus t over tau times e to the minus I omega t, and we integrate with time. Okay. So we have a v naught, and we can combine the exponentials. E to the, let's see, minus 1 over tau plus I omega times t dt. Okay, again, this is a relatively simple integral to evaluate just because it's an exponential. And so we're going to get minus v naught over 1 over tau plus I omega. And then we have e to the minus 1 over tau plus I omega times t. And we have to evaluate this between the limits of... Oh, sorry, I've made a mistake here. Let me fix this mistake. I substituted in this f of t, but the expression I put in for f of t is valid only for times greater than t equals 0, because at all the negative times f of t is 0. So we have to, once we substitute in our expression for f of t, we have to be careful because that's valid only for positive times. All of the negative times in that integral make no contribution. And so I have to fix this lower limit. Okay, and then when we evaluate our integral, we evaluate between the limits of 0 and plus infinity. Okay, and so let's just put in those limits of integration. So we're going to get a minus v naught 1 over tau plus I omega. And let's see, we have at the limit of plus infinity, we have e to the minus infinity over tau times e to the I omega times infinity minus, when we put in 0, we get e to the 0. Okay, so, well, okay, a couple things we can do. E to the 0 is just going to be 1. E to the I omega times infinity, well, if we think about that, e to the ix we could write as cos x plus I sine x, and the cosine and the sine functions are going to oscillate between plus or minus 1. So we don't know what this e to the I omega times infinity is going to actually evaluate to, but it's going to be something that's going to be between plus and minus 1 with a real component and an imaginary component. Okay, on the other hand, e to the minus infinity over tau, no matter what tau is, as long as it's not 0, well, as long as it's not infinity, let's say, this exponential is going to go to 0. So this goes to 0. And so 0 times something that's between plus and minus 1 and plus and minus I times 1, plus or minus I, that's all going to be 0. And so what we're left with in the end is that this f hat of omega, the Fourier transform, is going to be the minus v in front of the v naught cancels with the minus 1 in the square brackets. And so we just get a v naught 1 over tau plus I times omega. Okay, and just for cleanliness, what I'm going to do is I'm going to multiply the top and bottom by tau. And so we could also write this as v naught times tau divided by 1 plus I omega tau. And so that's our Fourier transform. And so what I said I was going to do was to talk about, like, what does it mean when f hat of omega is complex? Okay, so first let's just make a note of that fact. Note that f hat of omega is complex. Well, whenever we have any complex number, we know that we could write it in multiple ways. We could write it as a real component plus I times an imaginary component, or we could write it as a magnitude times a phase factor, e to the I phi. So we can write any complex number or any complex function as a magnitude times a phase factor. Okay, so for example, we could take, well, here, let's start on this page. Z, an arbitrary complex number is Z plus, sorry, I've been using I times Y. So a real and imaginary part. And so that could also be written as the magnitude of Z times the phase factor e to the I phi, where Z is equal to the square root of x squared plus y squared, and the tangent of the phase is equal to y over x. Okay, so that's fine. So let's see what happens in the case that we're working on. Our f hat of omega was equal to v naught times tau over 1 plus I omega times tau. So what I'd like to do first is move the imaginary part of this expression, the I omega tau, from the denominator to the numerator. And we can do that by multiplying the top and bottom by the complex conjugate of the denominator. And so we're effectively just multiplying by 1, but it allows us to re-express our function in a way that might be convenient for us. So in the numerator, we just get the v naught tau times 1 minus I omega tau, so I don't do anything with that. But the denominator, if you work out all of the terms, the cross terms end up canceling, and we get a 1 plus omega times tau squared. Okay, and so this lets us separate f hat of omega into its real and imaginary components. So the real component would be the v naught tau times 1 divided by 1 plus omega tau squared. And the imaginary component is everything that multiplies the I. And so that's going to be a minus v naught tau times omega tau. And then we still have the denominator. Okay, so why is this useful? Well, it's useful because now what we can do is we can immediately find the tan of phi if we were to express our f hat of omega in terms of a magnitude times a phase factor. The phi in the phase factor, or the tangent of that phase, would be y over x. When we take that ratio, the v naught tau and the 1 over 1 plus omega tau squared all end up canceling, and we just get a minus omega tau. And so the important conclusion from this part of the analysis is that notice that the phase changes as the frequency changes. Right? Our tan of phi depends on the value of omega. And so as we scan through the different frequencies, they're all going to have a different phase. And so that means if we want to construct our pulse in time for this particular function, we have to add up all the relevant frequencies, but they're not all going to add up in phase. They're not all going to peak at the same time. They'll be shifted relative to one another, and we have to do that, get that phase factor right for all the different frequencies. If when we combine them, we expect to get that the appropriate function of time, the appropriate pulse in time reconstructed. Okay, so the different frequency components of f hat of omega all have different phases. So that's what it means when we find an f hat of omega that's complex, right? If we found an f hat of omega that was purely real, then when we write it in terms of its real and imaginary component, it would be the real part plus I times 0. So the y would be equal to 0. And so then when we go calculate the tangent of phi as y over x, if y is equal to 0, then the tan of phi will be 0, And there'll be no frequency dependence, and so when we add up all the different frequency components, they'd all add up exactly in phase. Okay, so anyways, that's our interpretation of the meaning of a complex f hat of omega. Just to finish this off, let's also calculate the magnitude of f hat of omega, which we know is going to be x squared plus y squared, all square rooted. So f hat of omega squared is going to be x squared plus y squared. And let's see, both x and y have a v naught tau and a 1 plus omega tau squared in the denominator. And so when we square all of that, we're going to get v naught tau over 1 plus omega tau squared. So we have to square all of that. Both x and y have that factor when we square them. That's all of x, so we're just going to get a times 1 plus, and then the y has a minus omega tau in addition to all of that, and we have to square it. So the minus sign doesn't matter. We just get an omega tau squared. Omega tau squared. And so what's nice about this is that we get a cancellation. We can cancel this 1 plus omega tau squared with, one factor of the 1 plus omega tau squared of the denominator. So if I cancel that square, I just have to make sure that we keep the numerator squared. Okay, and so then what we're left with is that f hat of omega magnitude squared is going to be v naught over tau squared divided by 1 plus omega tau squared. And so that finally, if we were looking for just the magnitude without the square, we would get v naught tau over square root of 1 plus omega tau squared. Okay, and so that's the magnitude of our Fourier transform. Let's just plot that and see what it looks like. So here's a frequency axis. Well, in fact, actually, let me make this axis omega times tau. And so this will be f hat of omega magnitude. So if we go to 0 frequency, we set omega equal to 0, we get v naught over tau divided by 1. And so we'd have a v naught times tau over 1. So there's v naught times tau. Now, if we were to make this a log-log plot, what this function would look like is it would be roughly flat, and then it would start coming down once we crossed some kind of critical value. And that critical value would turn out to be, when we have an omega tau axis, that critical value is 1. And so 1 sits somewhere along here on our horizontal axis. And if we put omega tau equal to 1 in our expression, then we would get v naught over tau divided by the square root of 1 plus 1. And so it would be the square root of 2 in the denominator. And so over here we have a v naught tau over root 2. Okay, and so the function would look approximately like what I've drawn if we made our plot on a log-log scale. And so again, you may recognize this, in fact. This looks like a low-pass filter. So if you were to build a low-pass filter out of an RC circuit, the output voltage divided by the input voltage would have exactly this kind of shape. So that's kind of interesting, because when we started this, we kind of thought that, our pulse in time, this exponential decay, looked a little bit like resembled a RC circuit discharging. So something in the time domain, discharging capacitor through a resistor. And then when we took the Fourier transform, it again resembled some kind of behavior that we already know from, again, RC circuits. This time in the frequency domain, if we were thinking about what frequencies are passed by this filter, it ends up being a low-pass filter. So this resembles a RC low-pass filter in the frequency domain. And so you begin to see how some of this Fourier analysis is really useful, because we could start to connect it to things like that we know. We understand RC circuits in both the time and frequency domain, and now we have this mathematical tool that allows us to go between these two domains quite easily. Finally, let's just notice one last thing, and then we'll stop here. In some of the previous examples, we saw that when we have a narrow pulse in time, we get a wide range of frequencies. And so let's think about what a narrow pulse in time would mean in this example. If we made tau small, our exponential decays quickly and we have a narrow pulse in time. So in this example, a small tau, this would be like an RC time constant, for example. If you have a small RC time constant, your capacitor discharges quickly. A small tau corresponds to a narrow pulse in time. So this is like our f of t behavior. And so let's see, the range of frequencies passed by the magnitude of f hat of omega is determined by omega tau is equal to 1. So let's just write over here. Omega tau is equal to 1, kind of corresponds to the range of frequencies that are needed to reconstruct our pulse in time. And so that means omega goes as kind of 1 over tau. So if we made a narrow pulse in time by having a short tau, then the range of frequencies needed to correspond to that pulse in time is very wide. So a small tau corresponds to a narrow pulse in time, and a wide range of frequencies proportional to 1 over tau in f hat of omega. And so that's consistent with the previous examples that we saw of the box function and the delta function. Of course, the inverse of that is true. I won't write it down, but if we had a large tau, we would have something that decays slowly in time, so a wide pulse in time, and that would correspond to a narrow range of frequencies in f hat of omega. Okay, thanks very much. So those are several examples of some Fourier transforms and one inverse Fourier transform. So with that, I'll end the video and talk to you later.